Awesome. Thanks.
Okay, you came really at the right time. Yeah, so it's actually a pleasure to introduce Tianyi from Yale University. So he will be actually talking about everything, embedding and machine learning, maybe not dynamics, right? Dynamics will be mostly by the second speaker this afternoon. And yeah, so he will talk about spectroscopy from quantum embedding and machine learning. And let's thank him.
All right. All right. Thanks, Sagi, for the invitation. It's great to be here. It's the first time to be in the center. It's a nice environment. So today I'll be talking about some work we did on predicting materials spectroscopy. So part of this work is from my postdoc when I work with Garnet Chen at Caltech, and part of this talk is new, generated by the student and postdocs in my group. Okay. All right, so here's a brief overview of what we're going to do. So I'm going to give an introduction about what spectroscopy properties we're going to be talking about in this talk. And more specifically, I'll introduce the concept of Green's function a little bit. And then we're going to be talking about one specific type of quantum embedding called the dynamical mean field theory, or DMFT. After that, I'll be talking about some more recent developments in my group. That's with two more specific examples of problems. And finally, I'm going to be talking about a little bit of machine learning development, also very related to all of this. Okay. All right, some introduction. So I guess it will be helpful to first set up the discussion with some systems in mind. So the systems that we are particularly interested in is more strongly correlated systems, meaning that electron-electron interactions is very strong in certain type of materials, or specifically we'll be focusing on solids. There are many known quantum antibody effects in solids. For example, the most famous one, high TC superconductivity, and metal insulator transition, and more recently, topological materials and things like that. Okay, and when we talk about this kind of materials, typically we're talking about transition metal solids most of the time. And these materials are normally with open shell, 3D or 4F electrons in it. And that makes them strongly correlated. And what makes them unique is that they exhibit certain type of exotic quantum phenomena due to the interplay of all kinds of degrees of freedom, spin, charge, and orbitals. Okay, and here is a very sort of simple diagram that shows what methods one might use for this kind of task, simulating correlated electron solids. We know this is difficult, and if you look at computational complexity against accuracy, typically what's commonly done is that in 90% or 95% of cases, people do DFT. And sometimes people do GW, which is also called many-body perturbation theory. And there are all the other methods that people are interested in applying it to solids. For example, a couple cluster, quantum Monte Carlo, or even more like towards the exact end, PMRG or exact anglization. But of course, we know that these are very expensive and typically not possible to be done in the thermodynamic limit, meaning that when you simulate the solids, you can't just take a small fragment and simulate it. That result typically doesn't mean anything. You need to simulate the system, the periodic system, using dense enough K-point sampling or a very large supercell equivalent. Okay. on the other hand, if we just stick to DFT, it is great for many problems. And probably for many problems interested in chemistry, you don't need many things beyond DFT. But for correlated electron solids, DFT are not as reliable. For example, some very typical example is for mud insulators, meaning that for nickel oxide, for example, right? This is nickel oxide crystal. If you apply a DFT like PVE, you will get a prediction. You predict it to be a metal without a symmetry breaking of the spin channels. But in experiment, it doesn't matter what spin phase you are, you always have an insulator, right? And another more extreme case is the following. If you simulate something called condom physics, that is a very prototypical problem in condensed matter physics, where you simply have a sort of impurity in a bulk metal, and you simulate its spectrum. What it should be like is the black curve. You have a very sharp peak in the center, that is its density of states. Instead of that, if you use any mean field method, no matter what DFT functional you're using, you will get a curve like the red curve, which is much broader than this sharp peak in the center. And you don't have any features, essentially. You only have one peak, essentially. That's the other failure of mean field method. Okay, so following this, right, we're going to be focusing on some aspect of simulating solids. We're not going to be talking about everything about it, or we're not going to be talking about ground state energies in this talk. Instead, we're going to be talking about the charge excitations specifically, meaning that we're going to be focusing on photoemission spectroscopy. This is the one of the fundamental techniques to detect electron structure in solids, or if you know what is a band structure or energy levels in your materials, that is this type of this spectroscopy will give you. And more specifically, the most advanced technique is called ARPES, angle resolved photoemission spectroscopy, that can give you momentum dependent photoemission spectroscopy, which is what physicists are using. Okay. But from a more or simpler molecular orbital picture, it is merely just saying removing one electron from my sample. Then from that spectroscopy, I can infer the energy levels of my occupied orbitals or energy levels of my virtual orbitals. I plot it out. It will be this kind of density of states, right? And if I map it according to what momentum I can have a band structure with momentum label. Okay, it's the same thing as what chemists measure ionization potential, electron affinity. And certainly, ARPES is very useful. When you use ARPES to measure this kind of momentum-dependent spectral function, you can actually tell a lot of things about your materials, whether you have a superconductivity gap or whether you have a topological materials. That's why we're interested in simulating this kind of spectrum. Okay, so now some theoretical aspect about simulating photoemission spectroscopy. So this is called Green's function. So more specifically, we're just going to be focused on one particle Green's function, meaning that we care about the propagation of one electron or one hole in a many-electron system, and how that electron or hole travels from a certain time t2 to another time t1. Okay, and that propagation, that probability is given by this equation. It is simply a creation operator and an annihilation operator with a time ordering, and this psi is just a wave function, ground state wave function. Okay, if you can do that, you get a Green's function. Okay, Okay, so of course, this is rather abstract. This is in time domain, but typically what we measure in photoemission spectroscopy experiments is in frequency domain or in energy domain, right? We really want to map out the spectrum using energy x-axis. So that's why now you can also Fourier transform this thing and formulate it in a frequency domain. And what you will get is this kind of equation, right? Essentially, here, what you need to compute is an inverse of Hamiltonian and dotted with either n-1 state or n+1 state. So you see if you use a annihilation operator acting onto your wave function, you get n-1 state. So this will be actually the n-1 part. This will be the n+1 part. So this is how you can get charge excitations from Green's function calculation. Okay. So from there, you can directly get spectral function as what we measured, what people measured in experiment. So they're one-to-one corresponding. And or you can see the spectrum looks like this. And the thing that you can use any quantum chemistry method to compute Green's function, right? You can, if you plug in a Fock matrix here, that's a mean field Green's function. You can do a Green's function calculation for DFT. That's not a problem. But you can also plug in a much more complicated Hamiltonian. For example, if you plug in a Fuseli Hamiltonian, you will get exact Green's function. And but the difference between a mean field Green's function or what we call non-interacting Green's function calculation is that in a mean field Green's function calculation, you always get a delta-like peak whenever you calculate your state. But in reality, in correlated electron materials, in addition to a main quasi-particle peak, what we call quasi-particle peak, there is typically also satellite peaks, which is this broad kind of broad but lower spectrum showing up because of collective electron excitation in your solids. And those can only be captured by a manual method. Okay, I'm gonna use one more equation to define what's connecting these two, which is Dyson's equation. Essentially, you can actually connecting any two Green's function, maybe one at non-interacting level or mean field level, such as DFT, one at interacting level, for example, Fuseli, cluster, and so on, by using a term called self-energy, right? And this self-energy term essentially is the difference between these two Green's functions. And you can think this thing as a exchange correlation potential in DFT. However, it has a frequency dependent now. So it is sort of a dynamical exchange correlation potential. And that's what a self-energy is. Yes.
The exchange correlation kernel is also frequency dependent. I mean, should be.
Should be. Yes. Yes. Good point. Okay. All right. So I'll give you an example. What we can do if so. Like traditionally, right? As I said, people normally use DFT to simulate materials. For most of the weakly correlated materials, DFT is great. And more recently, there is increasing interest in the community, especially in the quantum chemistry community, to push the use of quantum chemistry methods for condensed matter systems. Because we know how to use a hierarchy of high accuracy methods for simulating molecules. The natural question is, can we do the same thing for solids and get a more systematically improvable framework? Okay, so there are many such methods, and I'm just going to show you one of them, which is done by us. And this is a recent work where we did formulate a couple cluster Green's function for periodic systems. So essentially, what we do is just to use pretty traditional couple cluster method, namely EOM CCSD, and we recast it in Green's function formalism and with K-point sampling. Then you would be able to use that to simulate some simple solids, for example, silicon crystal or slightly more complicated zinc oxide. Okay, so here just showing you what's the capability. We can do band structure calculation, or we can calculate density of states. So how to read this kind of two plots, as they will show up later. So this plot is y-axis is energy. It tells you the energy levels. But you see this weird indices here, L, gamma, X, W, K. They're momentum labels. Essentially, it tells you the momentum associated with the electron in your crystal or in your Brillouin zone. And you can see it as a crystal symmetry label. But essentially, there's no other specific physical meaning about these labels. Okay. Or sometimes we may plot this kind of thing, which is easier to understand, where the x-axis is energy, y-axis is density of states or intensity. Essentially, what this plot tells you is that your HOMO is here, your LUMO is here, and you will have more states. These are all the virtual states. These are all the occupied states. Right? That's about it. That's about these two pairs. Okay. So the good thing is nowadays people can simulate solids with sort of high-level quantum chemistry method, but the bad news is you can only do it in some very limited size. By limited size, I mean either very limited K-point sampling or very limited supercell size. You can't do very large because their scaling is too high. We know that CC scale as n to the 6th power. Okay. So natural question would be, what are the ways we can achieve this with some efficient algorithm design? And one of the ways that I'm going to be talking is quantum embedding. Mikhail talked about this embedding already in the context of subsystem DFT or DFT embedding. And here, rather, I will be talking about something in the context of range function embedding. And more specifically, I'll introduce a PyCF-based quantum embedding infrastructure for doing this kind of calculation. Okay. All right, so very basic introduction about quantum embedding for solids. Imagine that, so we should first set up our target. Our target is we want to be able to do this kind of calculation for solids and get a spectrum prediction. However, we want to do faster through quantum embedding. And our starting point is always a lower level theory calculation. And in this talk, most of the case, we'll be using mean field methods such as Hartree-Fock, or sometimes we'll be using a more expensive many-body methods that is GW. But let's say Hartree-Fock for now, which would be much simpler. All right. And what we're going to do is we're going to break them into fragments. And imagine that this is a periodic system, so that actually these fragments are all the same, right? They have the same periodicity, so they're all the same, actually. Then I can just focus on one of them. If I focus on one of them, I'm going to call this one impurity. The rest of the lattice or the crystal, I'm going to call it environment. And next, what I'm going to do is I am going to compress the information in the environment and derive an embedding Hamiltonian, meaning that I'm trying to simplify this large infinite crystal into a very small or finite impurity bus system. This bus contains the information in this environment, but its Hilbert space is much smaller than the original problem. In that way, if I can find a way to compress the environment, right, then I will have a much smaller object to work with, then maybe I can apply some high-level calculation to it, maybe couple cluster, maybe even more expensive things. And then I will need to give some feedback to the original low-level problem. That means we need to compute certain type of physical quantity here. It might be density, might be density matrix, might be Green's function. And if we can compute such physical quantity, we can give that high-level quantity as a feedback to the original problem and to improve the description of the system. Okay, so this is a very general description of what I mean by quantum embedding. Okay, why this might be useful? Because first, obvious thing is it can enable using high-level many-body theories for solids in a very large infinite size, or what we call thermodynamic limit. And then this kind of construction, right, we're trying to maintain certain quantum mechanical coupling between impurity and Bose states so that we can still capture certain type of exotic quantum mechanical states that cannot be captured at DFT level Hartree level. Okay, so a lot of different type of this kind of quantum embedding actually exist. One of them is density matrix embedding theory, or DMET. And what I'm gonna be talking about is another thing, which is dynamical mean field theory, or Green's function embedding. And more specifically, I want to focus on how to do ab initio calculation using that kind of framework. Okay, so same plot, but now changed to DMFT. What are the procedures to do DMFT calculation? The thing is the following. When we say we do low-level calculation, we actually calculate the mean field Green's function, which is very simple. You can just solve a DFT equation, and then naturally you get Green's function at DFT level or Hartree level. Next step is the following. I need to compress environment, and in the Green's function language, what we're going to do is we're going to use some term called hybridization function, which I'm not going to define here because it will be a long discussion. This term naturally is reflecting the environmental delocalization effects on this impurity. This is a frequency-dependent matrix, essentially. What you need to do is you need to discretize the thing into a series of baskets. And then you can form an embedding Hamiltonian that consists of impurity part, Bass part, and impurity Bass coupling part. And remember that this embedding Hamiltonian will be a much smaller thing than the original full Hamiltonian. And when I do the high-level calculation, what I'm going to do is I'm going to calculate the many-body Green's function using my favorite method. And then the important thing is I need a self-energy, which is the potential that captures the many-body effects. And yes.
I just want to know more about this delta.
Okay.
But I'm wondering, it depends on the Green's function of the environment, correct?
Yes. So delta is.
Yeah.
Now I need to guess which one is the. Okay.
Not that one. Yeah.
Not that one.
Yeah.
That must be this one.
Yeah. Let's throw those away.
Oh yeah, this one. Okay, the delta term is the following. It is just the G impurity inverse minus G problem inverse. But this thing is I'm gonna calculate it. So this thing is that you take your impurity problem and calculate the G. And this thing is, imagine you have the full G, you take the G block and inverse. And this two difference tells you the environmental effects, or that is called delta. That
Yes, no, I understand. I think I would see it better if it wasn't with the inverse, but with the, I guess the inverse of delta would make more physical sense to me, because then you see the coupling of the Green's function with the of the impurity with the environment, perhaps? Which would be the off-diagonal element of the big matrix.
Oh, I see. Good point. You mean just the off-diagonal element?
Right,
here.
exactly, exactly.
Good point. I'm gonna use that in the second part. Yeah, good point.
So that's the definition.
Of delta,
Yeah,
of hybridization, yes.
Yeah.
That is the definition.
but then you have to make approximation to G.
Yes.
Yeah.
G full starts from the FT level or Hartree-Fock level.
Okay.
Then that gives you the hybridization function at Hartree-Fock level. You
Yeah.
start from there.
Yeah.
And you need to run this whole thing self-consistently. Then you will update your G full
Okay.
using your manifolding methods. You get a better description of delta, and then you iterate it until you converge. Yeah. Okay. So I need to finish this loop. So the lower end of the loop is very important. It is saying I am going to use the many-body correction here, which is self-energy, to correct my original description of my solid, which is I'm just saying that the K-dependent self-energy is just equivalent to this impurity self-energy. Note that this is an approximation. There's no way this is true because this is essentially ignoring the K-dependence, or corresponding to a supercell perspective, this is ignoring all the off-diagonal self-energy term or off-diagonal self-energy correction, or essentially this is a local correction. It works perfectly when you have a purely local interaction. This approximation becomes exact, but we all know in realistic system, there's no such pure local interactions. Then this becomes only an approximation, right? Okay. Okay, so what we're gonna need to do is to do this thing self-consistently until some convergence is achieved. Okay, and as I said, the success of the MFT really relies on the assumption that electron correlation is local, right? But we also know that in transition metal systems, the 3D electrons, the 4F electrons, they are indeed local. Their interactions are mostly local. And that is why the MFT has achieved a very big success in condensed matter field or community. So this work was developed 30 years ago already by Anton George and Gabby Collier. And it's obviously old theory. And then the question becomes, why do we care after 30 years to improve the MFT in any possible sense? Okay, so this is because the Euro formalism for the MFT in doing solid state calculation is not necessarily the best formalism one can use. So this is so-called downfolded embedding or downfolding formalism. What people are normally doing when they are doing DFT plus the MFT calculation is that they first calculate the band structure of a material like this using DFT. And then they take the low energy bands. You can take, say, 5 bands or more bands and to try to do a downfolding procedure through constrained DFT or constrained RPA to essentially derive a model Hamiltonian, right? So this will be a 5 orbital or even 1 orbital model Hamiltonian where you have a very strong correlation within this correlated subspace. And also you only have one or few parameters describing your interactions, right? If you know Hubbard model, you know that there is a U parameter describing the on-site interaction within an orbital, and that essentially is what this one is. Normally you derive a Hubbard model like Hamiltonian here, and you solve this. Okay. The benefit of that is you will have such a small problem, you can solve them exactly in many cases. But there is also issues. The main issues is that this kind of downfolding introduces uncontrolled errors in this Hamiltonian because you are using approximated procedure like constraint EFT or constraint RPA, there is bias encoded in the small impurity space or Hamiltonian, right? And there are also studies showing that your results could be very sensitive to how you choose the spans to do the downfolding. There are one recent paper showing that you can predict correlation strengths across several folds by just changing what orbitals you're choosing. Everything else can be the same, but you can still get random results for a material. And the third thing is less of an issue, but still, your intermediate range correlation. We're not even talking about long range interactions. We're just talking about the interactions beyond these 5 orbitals. They are treated at a lower level of theory, DFT or GW. Sometimes that is a pretty good assumption, but not always a good assumption. All right, so what we want to do is different here. We want to do something more quantum chemistry driven, meaning that what about if we just treat a much larger Hilbert space by choosing, say, all orbitals of all atoms of a given cell as our embedded fragment, right? That is really a chemistry thinking. Just choose whatever fragment you want to treat and do the MFT, right? There's no downfolding associated with that. And that being said, you're going to be treating a much larger impurity problem, probably up to 100 or a couple hundreds orbitals. And the Coulomb interactions between all of these orbitals are just general Hamiltonians that you calculate from your 2-electron intergroups, and nothing special about it. All right, so what we want to achieve is apparently quite different from what has been done in the DMFT community, and we need to test, can one really achieve such a framework efficiently? And if so, what kind of high-level quantum chemistry method one can use to solve this problem in this formula, right? Okay. All right, so what we do is we develop a quantum embedding infrastructure or code, which we call full cell quantum embedding, or sometimes we call them orbital quantum embedding. In following this idea, and we base our all developments on Picea, which means we use periodic Gaussian basis instead of plane wave basis. We figure out ways to efficient integral transformation from a large crystal basis to a few hundred orbitals, local basis, and localization, this kind of thing. And there are more specific embedding related algorithms. For example, how can you really discretize this hybridization function into Bath states, deriving Hamiltonian and solve it using Green's function solvers. Those are packaged into FCDMFT, or there's another package for density matrix embedding theory called LibDMAT. Okay, so now I'm going to show you some results, just focusing on DMFT. See how much time I go. All right. So first thing I'm going to show is actually not a strong correlated material. It's rather just a weakly correlated material, but it's more like a sanity check, right? We need to make sure the embedding algorithm works well when we have some benchmark that we can rely on, which is a full couple cluster calculation of the band structure of 2D boron nitride. So this is a 2-dimensional boron nitride. We only do a relatively small K-point sampling. That's because this is a size that you can get a full couple cluster working. Beyond that, it's going to be expensive. So we just stick with a small K-point sampling size for this 2D material. And we start from Hartree Fock as our low-level theory. And most of you know that Hartree Fock is very bad for solids. And band gap errors many EVs typically. All right, so what we do is Hartree-Fock plus DMFT calculation using just one unit cell as our impurity, meaning that we are breaking this whole 2D sheet into many fragments. Each fragment has 2 atoms in it. And the errors is dramatically reduced to under 0.25 EV. And if you look at the band structure comparison, where the heat map here is Hartree-Fock plus DMFT, the black dots here are the reference values, CCNC values. You see the comparison is pretty good, not perfect, but pretty good. That means that this good sanity check, meaning that this algorithm more or less work at least for 2D programs, right?
I have a question. So,
Yes.
wait, so how many electrons are you actually treating? You said I thought you would treat the whole atom within this methodology. Are you treating only 2 electrons you said per site?
2 atoms.
Okay, and you have all the full electrons there and you're treating them exclusively.
Yeah. So
Okay.
these 2 atoms are like, of course, in a Gaussian basis, not very large. 2 atoms only say 30 orbitals and maybe 10, because here, you know, it's only 8 electrons actually, only 8 units electron. Yeah, so it's not that large. Yeah. But of course, remember that you're not only have impurity, you also have Bass states. Those Bass states carry electrons as well. Now, you see that this kind of Bass states mimic chemical bonding. So that gives you a chemical bonding environment for solids. So plus that, you will actually have many more electrons than just 8.
Okay, and the other question is, how come they visiting the starting point? Why are you using Hartree-Fock specifically? Is there a reason, or is it just?
Oh, it's because it's simple.
But the result would be affected substantially, I guess, based on the initial guess, or not really?
Hartree-Fock is the worst possible case you can start with. Right?
Yeah.
Yeah.
I'm just wondering because, well, okay,
So if you use a better method, it will likely be better error cancellation. And I would argue the errors would not be larger, would more likely be smaller. Yeah.
well, okay, but the experimental bang up here is around 6.4, right? Is the experimental bang up here?
Oh, you mean for 2D Bornite, right?
Yeah.
Yeah, good question. Because we are only doing a very small K-point sampling. We're not doing an infinite K-point extrapolation. That's why all these values cannot really be compared to experiments. It's merely a numerical check. Because you can imagine what is a perfect embedding method is it reproduces the full supercell many-body calculation. That is the perfect embedding method, at least within the geometric concept, right? Yeah. If you reproduce that, your embedding algorithm is great. If you cannot match the experiment, that means the many-body method is not good enough, right? And that's another story. Yeah. So there are several factors one need to check. So this is checking one factor. That make sense?
Yeah.
Okay. So next we do a more strongly correlated material, nickel oxide. This is a very prototypical correlated material. So at room temperature, it is antiferromagnetic, meaning that for nickel on this plane and for nickel on this plane, they have different spins, right? They have spin up here, spin down here, and up, down, depending on form. Okay, so here, Hartree-Fock plus DMFT, I didn't show it here. It's pretty bad because Hartree-Fock is so bad. For any 3D solid, actually, Hartree-Fock is very bad. For 2D, it's actually not that bad. For 3D, we have stronger screening effects. Hartree-Fock is so bad. So that's why in this work, we choose to develop a further algorithm called GW plus DMFT. And this is also proposed in the DMFT community, I would say about 20 years ago already. But only within the last 5 years, there are mature developments or implementations coming out. Okay. All right, so you can see that if you start from PBE, it will have a band gap because now you allow the spin symmetry breaking, then you will have a band gap, although much smaller. Doing many-body perturbation theory on top of PBE doesn't really correct it. Typically, for weakly correlating materials, this GW at PBE is very good. However, for nickel oxide, it is not. Then what we do is on top of this, we do a DMFT calculation using, again, cluster as our impurity solver. And this is the result. So the band gap is 4.0 eV, much closer to experiment. And what we can also compare is to the experimental full emission spectrum. Here you can see there are several agreement and disagreement. Agreement is that, of course, the main valence peak are okay. Now, I would not say perfect, but you see there's a 2-peak structure here. You also have 2-peak structure here. Band gap is good. The conduction band is okay. But you see a peak here that's not detected at all in this region. That is because of the specific that is because of specific photon energy you use in photon emission experiment. If you go to a lower photon energy, measure it, that reveals more of the oxygen 2p peak, you will find our prediction here is actually pretty good agreement with this. And if you go to the orbital resolved dots, you will see this is indeed mainly dominated by oxygen 2p. Okay, so this is okay, so this is
Sorry, I have one more question.
Yeah, sure.
Do you happen to know how bad or well does VFP plus U, just literally just PV plus U dot in this?
if you use a good U, you get very good result.
But that's what I thought, but this is much less expensive, right?
Yeah, much less expensive. But you need to know what is a good U. Yeah. So I wouldn't say DFT plus U is bad for this, because typically you can choose a reasonable U, get a reasonable result, right? Yeah. But still, it's has that empirical dependency.
I have a question about, are these two the same coefficient?
Which two?
The left one band gap and the right dots,
Oh, sure. Yes.
but from the right side, since the band gap is not almost.
Oh, because in experiment, people are measuring band gap using the mid height to measure the band gap. Because of their resolution, it's not high enough. So what they are doing is they measure the difference between this point and this point. They measure this energy difference. in
Okay, so the
experiment.
GW plus DMF, they also use that.
Yeah, we all measure the same way as the experiment.
Maybe you can help me understand what kind of system environment correlations you include with your delta. Like
That's a,
what physics do you put in there?
okay.
And which is important for band gap? If you know, I mean, if it is known, right?
I think the most important, that's a good question, is essentially you want to reproduce your range function from your empirical calculation at many-body level. The nice thing about delta is you can define it at any level, even at a many-body level, you have the same definition. So by designing the baths in this way, to be a frequency dependent way, you are actually capturing the short range interactions surrounding the fragment at a many-body level. That's what I can tell.
Your G full, you don't compute the G full, right?
G2 is approximately.
Approximate. And so what do you put? Like you say you have some band orbitals. Can you say more about those a little bit, maybe?
Sure. You mean how do I get G2?
Yes.
I got G2 from getting sigma self energy.
But isn't that the difference between these two, sigma?
No,
Oh, no, that's
self energy.
Ah, sorry.
Now, so this is very tricky.
Yes, 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 because this is the impurity, this is delta.
There are two terms. So this thing You can consider this as a second self energy.
Yes.
That's capturing the delocalized. So this is a local. This is delocal. Delocal. Yeah, it's actually.
And G4, you compute it how? With what method? Not couple cluster.
It is. I'm calculating self energy using cluster, right? And G foo, you can just get G foo inverse from G0 inverse minus sigma. Sigma is calculated using the DMFT. And DMFT sigma can be couple cluster, can be Carbon, can be anything. Okay. Can even be Hartree Fock. There are people just using Hartree Fock as it turns out. Yeah. Did that sort out solve some questions?
It's getting me there. I'm like
Okay, good. Yeah,
starting to-
yeah, good.
So do you always get convergence when you do the iteration? So,
Do I always get convergence?
yeah,
Typically, yes. Not strictly tight, but typically to extent and my spectrum doesn't change. Yes.
so what's the criterion for convergence?
The criteria,
The condition when you get the self-consistent condition.
the condition would be your self energy doesn't change or
Yeah,
your delta doesn't.
How much it doesn't change is typically,
Typically, you take a 2 norm to be under 10 to the minus 3. I would call it convergence. Yeah.
And then the iterations normally, do you know how many iterations?
Normally, for simple calculations, 5, more difficult one, 10, no more than 20 in typical.
I see. So it-
Well, actually, model
Convergence
Hamiltonians
is-
is slower.
I see, yeah.
Been a while since I've worked on the team, which one's work coded up. But to my recollection, and I can't remember if it's delta or sigma, you actually have to do a numerical fit to your discrete.
Yeah,
But there was a numerical fit for one of these two parameters
delta.
for delta. And that, at least way back when I first joined Gart's group, that numerical fit was a real pain in the butt.
Yes. It's not as a pain now.
Okay, what did you do to fix that?
Oh, there are some more standard procedure which is fine.
Okay, so it's just better Python.
Yeah.
Optimizers.
There's no perfect ways to do that, of course. It's oftentimes a condition problem, especially for this kind of large matrix.
Mhm.
But then it's never a perfect fit. It's normally a minimization.
But it's not a, like it was, but that's not.
It's not a bottleneck.
It's not.
The bottleneck always is, as it should be, calculating sigma. Okay, now I'm gonna switch gear. I may want to. I have until 50. Right?
25 minutes, about 30 minutes.
Okay,
We
got it.
start 5 minutes. later, so
Okay,
yeah.
I'm gonna
So,
skip convo because kind of hard to understand. I'm gonna go to this. Okay. So there are problems existing in current formalism. There are 2 main problems. The first problem is that one can argue that couple cluster can be used for any strongly correlating materials. That's just not true because we know couple cluster break down for very strong correlation. And in those cases, you need something better. For example, multi-reference method or DMRG. So in this work that I don't have time to talk, we use essentially DMRG as our impurity solver to solve an old physics problem called the Kondo problem. There we're trying to predict certain characteristic parameter called Kondo temperature for a series of transition metal in bulk copper, which is a very strong correlation problem. But the nice thing there is the correlation is very local. So you don't need very large impurity size. Okay, that's one of the challenge where I'm gonna just pass on. And the second challenge is the following. As I said before, the success of the MFT relies on the local approximation. What if we just want to use it as a general tool to study solids? then we know that in many solid state systems, the interactions are not really always local. There are many longer range interactions, for example, in metal and in small band gap semiconductors, the correlation isn't really that local. Okay, then there is problem for ab initio DMFT because even for this case, this is 2D boron nitride again. I sort of hide this result from the first part. There's bad things about this. Okay, the bad thing about this is it's hard to improve systematically towards the full supercell limit, meaning that if you simply just increasing your fast state size or impurity size, it's not actually going to give you a better result very quickly, right? You expect to, if you increase the impurity size, maybe double it or triple it, you will go from 0.25 eV to within 0.05 eV, but that is not happening actually. And another bad thing is when we are doing this kind of embedding, we break translation symmetry artificially, because when you are choosing a certain fragment artificially, then you naturally break the translation symmetry in that crystal. That actually reflects on this density of state plot. If you just focus on the comparison here, right, on the valence peak. So this is a correct one. This is a UM6SD. You have one giant peak here, but you see in some DMFT calculation, you simply just break that degeneracy into several small peaks, right? That is artificial. That shouldn't be there. Even Hartree-Fock get it correct because Hartree-Fock doesn't have that artificial transition symmetry breaking. But you don't have it in any DMFT or maybe in this one. But as you increase your batch size, you actually get worse prediction for this peak. Okay, and sometimes, as Sally has just asked, you need several cycles or tens of cycles of self-consistency enforced, which could be demanding. Okay, so we need an adapted, like more improved algorithm to deal with this problem. So in order to solve this problem, we realize that the issue is really that the bass states, its coupling to impurity is really only one particle interactions. We're using a large number of bass states, but all of them are just coupled to the impurity through some simple one particle coupling parameter V, and also their energy levels. And all of these are one particle like, right? They don't have the two particle interactions as in the impurity Hamiltonian. So this is a really general impurity Hamiltonian. And naturally, one would ask, what if we allow this impurity Bass coupling to be a general two particle interaction as it should be? And the idea here is, what about we just try to abandon this delta? Instead, we go through a projection sort of algorithm, meaning that can we just think of a rotation matrix R that rotates the full Hamiltonian into an embedding Hamiltonian that is atom dependent? By doing that, you're guaranteed to not break the transition symmetry because now you do atom by atom simulation. But the question would be how you can get this rotation matrix, right? And if you can get this Hamiltonian, you just solve it. And again, use self-energy here. And you rotate the self-energy back to the full system to recover full self-energy. So this is essentially derive a rotation matrix, project it onto some embedding problem, solve it, and project it back to the original problem. It's like always projection based. Okay, so then this is the challenging part, which is what kind of batch construction you can get. So what we do is the following. We certainly take wisdom from the other embedding methods, namely DMET, where in DMET it's very typical that people just take the off-diagonal density matrix to represent the environmental effects. And that guarantees that you can match the impurity 1 REM at mean field level by doing impurity calculation. And that is one part of our states. And the second one is what Mikhail has asked, why not we use the off-diagonal Green's function information to derive fast states? And indeed, you can actually do that. And this is what we are doing in this framework. We just directly do using the off-diagonal Green's function information to derive a set of fast states. And finally, because our target is to be more systematically improvable, we sort of use the same idea that George Booth used in his 2022 PRX paper, where you can derive a set of MP2 natural orbital bases that couples you pick certain natural orbitals from the environment that correlated strongly to your impurity clusters. That is a third type of fast states that you can pick. Okay, and you can do a combination of the three, and that gives you a projection matrix. Okay, so this is a result that we get for 2D boron nitride again. So this time we really have a full CCGF result, not a UM-CCC actually, to compare to. And this is the old result, the GCTC 2020 paper. If you compare the band gap prediction, as I said, is pretty good, but then you see the degeneracy is like, in some cases miserable because you break the transitional symmetry. But using the new sort of formalism, you recover the band degeneracy almost perfectly, even if you still use Hartree-Fock as your starting point, right? The downside is now the band gap is a little bit larger compared to before. But I would argue that before we kind of get lucky to have some error cancellation that force the band gap to be good. And if we go up to GW, essentially you get the same plot. The GW plus IBDT is the same as full couple cluster result. And all of the three has the same impurity size essentially. Okay. So next one is metallic sodium. So this is really trying to test how we can deal with non-local interactions in metals, because we know that's typically the case. So I hope this is not too hard to see, but you can just directly see the number. Hopefully, this is thought to be a simple case even for LDA, because essentially, if you parameterize your DFT using a uniform electron gas information, you should be able to calculate like simple metal band structure to some good accuracy, which is indeed the case. LDA actually performs better than hybrid DFT in this case, where this outlier line is actually disregarded. It's the worst among all the methods you can test. Okay. But still, you get around 25% overestimation compared to the experiment, which is this curve. So what we're measuring is the energy levels of this point. So you may have 2.5 or 2.6 EV, or you may have 4 EV, depending on what method you have. Okay. And GW improves over DFT, but still you got 50%, around 50% overestimation. And as I said, we believe that electron correlation is weak, but why? If that's true, why LDA and GW are not giving like a better result? One typically expects the GW can be very good in this case, but it's not. Okay, so this is a simulation that we did on metallic sodium, and what we get is using CCST solver, and this heat map is actually the embedding result. And you see that it overlaps well with the black dots and the red curve. Both are independent of his experiment. And our error now is only 2 to 7% compared to experiment. Okay, so how many minutes do I have? Maybe 15 minutes?
Yes.
Yeah. Okay.
About 20 minutes.
Okay, good. Okay, so I'm gonna finish the last part relatively quickly. It's not that hard. So, the motivation here for doing any machine learning for many-body Green's function is that that's actually very similar like thought. We can do Green's function calculation to periodic systems, but what about I'm gonna do a very heterogeneous system? We may need to do hundreds, if not more, independent impurity calculations, which I simply cannot afford. Typically, sometimes I cannot even afford one such calculation using a limited resource, right? And naturally, the question is, if we want to apply the MFT to any heterogeneous system, say liquid water or say nanomaterials, is there any chance that one can do that, right? So, so that makes us think, can we do any type of machine learning to accelerate that? Okay. So the machine learning, this machine learning project is the following. We're thinking about the following object, which is actually a frequency-dependent matrix, which I call it a matrix-valued dynamical quantity. So essentially what you need to learn is actually a series of two-dimensional matrix on a frequency axis, which apparently is a gigantic thing to learn. But if you can learn that, you have access to photoemission spectra of molecules or materials at a given many-body level. And then, as I said, you can accelerate your Green's function embedding calculation for heterogeneous systems. And you may have connection to other electronic properties like density matrix or even neutral excitations. But the question mark would be how to learn such a thing, right? What we're doing here is instead of learning Green's function, why not just doing machine learning on self-energy? Because we know that the self-energy term captures the many-body effects between a mean field method and an interacting method. And that naturally gives you something that's delta machine learning, right? So it's very natural from Dyson equation, you have this delta ML formula. That's what we're going to do. What we're going to do is we're going to learn machine self-energy on the imaginary frequency axis, because there the self-energy matrix is very smooth. So you need much fewer points to represent your self-energy. And essentially here, what we are doing is just 18 points on the imaginary frequency axis. So essentially you have 18 such matrices to learn. Okay, so once you learn that, your prediction of Green's function would be on the imaginary axis by using the Dyson equation. That means you always need to have some mean field starting point. So for us, mean field calculation is always needed. And our target is simply to accelerate a correlated method beyond that. And once we learn this G on I omega axis, one can apply another trick, which is called analytic continuation, to obtain a real frequency axis G. And then from there, you can get your spectrum. Okay.
Okay, not to, be a bit of an annoyance here, but analytical continuation from imaginary time to real time is an ill-posed problem.
Yes.
So.
Yeah.
Right.
It is not well defined.
It's not well defined. So,
Yeah.
so how are you getting around that?
So the thing is depending on the nature of the system you have. If you have, and also the method you have. Typically for GW, on not so strongly correlated system, analytic continuation is pretty stable.
Okay.
That is why the mainstream GW methods, many are nowadays formulated in measuring time domain frequency. And but there's another problem. What if you are really learning something strongly correlated? then you will have a trouble there. You need a great analytical elimination method to help you get rid of this. But I would argue that is not the problem of this method. That's essentially the problem of any many-body Green's function method.
Well, I guess I'm reformulating it.
Because most methods are formulated in imaginary frequency or time domain, including couple cluster, quantum one column. Many people are doing that even without the machine learning trick. They're just doing that because that's cheap to do. Yes. But of course, you will lose some real access information. You will encounter situations you don't have stable AC. Both are correct.
So you don't, so there's no temperature effect in your calculation?
This is a zero temperature. Yeah, but one can naturally think a possibility of extending it.
Yeah.
If you have a final temperature method to start with.
Then you do something like maximum entropy method for analytic continuation or
Here we use Paddy.
okay.
Yeah. Yeah, speaking of which, we do encounter situation where we cannot do stable AC. We are exploring some other AC method, like the one that Emmanuel Gall and Yun developed recently, which seems to be promising, right? Which is more like noisy noisy resistance kind of.
Silly question. So I guess the problem with the real axis is that you have poles, right?
Yes.
So, but you can move away from the real, you can still be
Yes.
thinking, why don't you stay parallel to the real axis?
Yes.
But away from it, then your poles become,
Broadened.
and then they're smooth.
Yes. They're smooth, but not as smooth as imaginary axis.
Imaginary axis is just something that goes down. It's
That makes it easier to
washing
learn.
out
Right?
all the information. It's
Right. Yes.
because you're going this way, no? It's the poles.
Yeah. The nice thing about doing imaginary axis is that you can use really a small number of grid points.
Yeah. Okay. Yeah.
Like even 8 points would be fine,
Yes.
right? But for real axis, if you don't want to wash out too many information, you cannot use a very large Brownian. In that sense, you still need, I would say, 50 to 100 points to represent your spectrum, right? In some cases, there are people just to study machine learning tensor states at the FT level. Most of the work are done in real axis, and there you can learn something like 200 points or something. They can also get good result if you have large enough data. Yeah.
And is it important to get the poles? I guess so, right? You really.
It is important. You're right.
And which poles are more important? The lower energy poles, I'm guessing, for your, like the ones close to the band gap, right? The ones that are.
Yeah. That region, the near Fermi level region. Yeah. Those are good thoughts. Yeah. We haven't really tried.
Maybe you can do a mix of the two things, right? Maybe you can learn the poles nearby,
Oh, sure.
somewhere parallel to the real axis.
Sure.
Everything else.
That's a nice thought. Yeah. That's a nice thought. Okay. So we use kernel-rich regression, and what we do is actually we train independent KRR models for diagonal and off-diagonal elements. This is merely a choice. And on each frequency point, so you will have model like this, right? And you need some feature vector for your diagonal, off-diagonal self-energy elements. And what we did is we follow some pretty routine way, which is, I guess, started with Tom Miller's molecular orbital-based method. Here, what we're doing is in a rotation invariant local orbital basis represent all of our matrices. And I will argue what is new in this feature matrices is the introduction of dynamic homing field features on imaginary axis, which is really inspired by DFT. Say we put this hybridization term as our feature in machine learning. Okay. All right, essentially this is vector of 29 elements for each of this. Okay, I'll just show some results. I think I have maybe 5 minutes. So first is water monomers, simply saying. Here the thought is that we are not actually pursuing like highly accurate, meaning that like really tight energy threshold, because our thought is that if we cannot afford many volume calculation, probably we should just see if this method can be any useful using really a small number of data, right? Because we cannot really afford hundreds or thousands of high-level calculations, even for medium-sized molecules. Okay, so for this case, we're merely scanning a 3 by 3 by 3 grid of water geometry, and at 2 levels, GW or FUSI actually, we're predicting 2 representative geometry, one equilibrium, one really rather stretched, meaning that for equilibrium, which is this one, it's relatively weakly correlated. For stretched, it's rather strongly correlated. Okay. So we find that actually GW is pretty easy to learn. It's really because GW is not reflecting or capturing the stronger correlation in stretch geometry that good. That's why it makes it easier to learn. If you go to FUSI level, the agreement becomes less satisfying, but still you see the spectrum, the main peaks are there. There is some error, but not huge. And also you can see that in FUSI stretch geometry situation, you will have some orbital renormalization. See in these orbitals, they're not like nice quasi-particle peak. Instead, they are just broader peak because of the correlation. And here I'm just showing you the self-energy predictions. Pretty good. Okay. And next, what I'm showing you is liquid water. What we are learning is we're doing the following. We train 8 water and 16 water cluster on 1 AMD snapshot with PBC. We're predicting 64 water, and all of the things are done at GW level. Moving forward is all GW because FUSI you can't afford it in any realistic system. This again is pretty good. It may be harder to see, but I'll show you the result, the arrow metric here. So with that 8 plus 16 to predict 64, you will have some error for HOMO and band gap 0.15 eV, not so small, but well, acceptable to us considering we use too little data. And if you are willing to add a 32 calculation to predict 64, you get zero results across all regions, and the DOS prediction is also pretty good. The only discrepancy is in this deeper limits region. Okay. All right, and we did a more extensive study on QM7 and QM9 dataset. These are the organic molecules with under 7 heavy atoms or under 9 heavy atoms. And again, what we're doing is something non-traditional, because again, we want to say, if we are not able to afford the many GW calculation, what if we just pick some small molecules and a small number of molecules to calculate and predict all the other molecules, see what happens, right? There's no way these can give you like very low error, but how large would the error be? That's a question. Okay, so this is error statistics, also 10 random replicas from the sampling. And you see we have 48 molecules predicting around 2000. So we see that the homonormal errors are around 0.13 or 0.1 eV, band gap errors slightly larger, less than 0.2 eV. And I'm going to show you some DOS to finish this discussion. Okay. So this is a distribution of DOS error. Because this is a relative error on the x-axis, it doesn't mean anything. So what we do is we show some representative DOS from very good prediction, average prediction, and later I'll show you very bad prediction. Okay, so this is a very good prediction for a random molecule. I don't know how to call this, but you see that this is essentially exact prediction of its dots. And this is an average prediction. The shaded area is the true GW result. Blue curve is the prediction. It's not perfect, but still pretty good. Now I'm going to show you what is a bad prediction. Okay, these two are the bad predictions. So this is the worst dots. This is the worst band gap prediction. And worst dots prediction is actually not that bad, especially if you look at the HOMO and LUMO. It's capturing the HOMO-LUMO energy within a reasonable accuracy. The bad prediction is on the higher virtual side and sometimes lower the valence side. But it's just because our DOS metric penalize small molecules more. So we see that this one with 2 triple carbon bond has worse DOS. This is actually truly the worst thing that we predict from our model. It has the worst band gap. You see the band gap is completely messed up. Although it's still like closer to the true value compared to the starting point, which is PV 0, it's nowhere close to useful, right? And this is merely because, or we think it is because this object is a COO minus group here and an NH2 plus group here, which is a separate charge group. And we have nothing like that in our 48 training molecule. And that is why we infer that we have such a bad prediction. All right, with that, I'm going to conclude. Remind you that we have talked about 2 ways of accelerating many-body Green's function calculation in molecules and in solids. And these are the people who do the work in my group. Judge and the postdoc who do the embedding work, and then the students who do machine learning work, and another student who do the periodic cluster work. And the first half of the talk was done in Garnett's group, and with many Garnett's talented students. And with that, thank you for your attention.
Hey, thank you. Time for one quick question. So for the machine learning part, so if you try to train the real-time Green function approach, it will be too difficult.
It is possible.
Yeah.
But one just needs many more points and potentially more independently trained model. The question is, what we haven't addressed here is whether it is possible to put different frequency points into one model. Because here we are training different points separately as independent models, but which doesn't really reflect any connection between this different information on different points.
Yeah.
So one thing we haven't tried yet is what if you are trying to train one model for different frequency or time points? That might be interesting to learn. And yeah.
Well, good question about your color mine on the last slide. Yeah, on the right corner, why that point the color plot is not aligned?
Here?
Yes,
This region?
yes.
This is again what I call due to collective electron excitation that makes your nice delta peak broadened to be behaving like a satellite kind of peak, broadened peak. That's from electron correlation, I would say. So essentially at different symmetry points, you have different strengths of correlation. And it happens in sodium around gamma point, this region, you have stronger or smaller coulomb particle weight that essentially makes it not a delta function like. Yeah.
Okay, let's hear you one more time. So you have a short 4-minute break and then we'll meet again. Yeah. Now we'll start at 4 p.m.
Some ideas, lots of ideas. One press. Good.
It's interesting to think about whether you can gain more information from real access learning.
Very likely, yes.
Yeah.
I mean, just a trick, right?
It's
Okay, so we have now final speaker for today's workshop and another great theoretician from Chan's school. Yeah. So I think he has many different research activity programs now, but I actually asked him specifically about talking about this real-time simulations of non-equilibrium dynamics. And so let's welcome Joshua Kretschmer from Georgia Tech.
Thank you very much for the introduction and the invite, and it's a pleasure to be here. I haven't been to New York since I was a postdoc at Princeton. It's always good to be back here. I do enjoy my time here. So I will be kind of a little bit of an odd man out here, in that I will explicitly talking about dynamics, so looking at real-time methods. I will though talk about both DFT and embedding, though I won't discuss machine learning. I can actually do that in my group. But before I jump into the specific stuff I'll be talking about today, I want to just kind of usually tack on this slide at the beginning. So what do I do in my group? So what I personally am always interested in and have always been interested in is really looking at electron dynamics. So it's still what I do, and we really develop new simulation methods to look at electron dynamics in all sorts of complex systems. And so we do quite a bit of method development in my group, really pulling from areas of both quantum dynamics as well as electronic structure theory. So a lot of the techniques we use in my group, which I will not talk about today, are referred to as these classically isomorphic methods. The idea behind these techniques is they allow us to map a quantum mechanical system to some kind of more complex classical system, such that when we run a computer simulation, all we're doing is classical molecular dynamics, but we get out quantum mechanical information. And so we're using these type of techniques in the context of looking at, for example, charge transport in perovskite systems. We also dabble in this field of strong light matter coupling, developing these classically isomorphic methods to tackle some of those problems. So that's my kind of 1-minute pitch on that half the group. But I will not be discussing that today. If you have questions, feel free to come up and ask me what's going on with that side of the stuff. What I'll really be talking about today is really work in this area of real-time electronic structure theory. So we're taking ideas from electronic structure theory, but really trying to understand quantum dynamics. And I'm going to tell you effectively 2 stories today. One story is really looking at what happens in weakly bound systems following the generation of either a inner valence or core ionization event. And we're kind of basically throwing real-time density functional theory at this problem and seeing if it works and how well does it work. And then in the second part of my talk, I'll actually, and Tian, you gave a very nice introduction, so I'll build off of what he did, where we're really developing more, let's say, sophisticated techniques within this field of quantum embedding to really look at real-time propagation methods within quantum embedding. Where we're heading with that is to really look at the spin transport dynamics. And really in the context of something referred to as chiral induced spin selectivity, which very briefly, if you drive a current through a helical molecule, due to the helical nature of that molecule, that can actually impose a spin polarization to your current. And the underlying mechanism behind that is actually very poorly understood. You kind of charge through a coil picture, or just kind of a very basic Lorentz force or spin orbit coupling with the quantum mechanical is insufficient to describe that process. So we're really interested in deriving and defining new simulation methodologies that allow us to simulate that directly. So that's really where kind of the second half is going to. So yeah, so these are some of the things going on in my group. If you want to learn more, come talk to me. I'm happy to do so. But what am I going to talk about more kind of specifically today is really looking at non-equilibrium electron dynamics. So what do I mean by this? Well, non-equilibrium electron dynamics, this is really electronic motion that's kind of induced either due to some non-stationary initial state, so I'm not initialized to some kind of Born-Oppenheimer state, or because I just have some external bias driving my electronic system. Okay, that's really what we mean by non-equilibrium. Either I'm starting in a funky initial state, or I have some external bias. Now, one thing I do want to emphasize with what I'm talking about today, though, is I'm really just focusing on electrons. So I'm really going to be looking at electronic motion, even in the absence of nuclear motion. Now here it seems like we're mainly talking about electronic structure, so this isn't as big of a point to make, but this is really a comparison to, let's say, more conventional non-adiabatic dynamics talks, where you're really thinking about that in this nuclear motion that's inducing electronic transitions. That's not what I'm talking about today. I'm talking about kind of more complex physics, where we really have electronic motion due to some crazy event or crazy environment outside of just the nuclei itself. And really developing and asking questions about what methods do we need to tackle such systems. So with that in mind, what are we doing? We're really developing efficient and accurate methods for the direct simulation of the electronic wave function. So this is going to be my quantity of interest, kind of in all of these cases, is we're really just trying to solve the time-dependent Schrodinger equation. Okay, and both of these kind of parts of this talk are really getting at this in different contexts. So to start off in this first half of my talk, what I'm really going to be talking about is tackling this problem of electronic decay mechanisms and really asking this question: what happens when an inner shell electron is ionized? So this could be an inner valence or a core electron. Here we'll really be focusing on kind of inner valence ionization. Now, a few things can kind of happen. First, let's draw this very simple MO picture here. I have a bunch of occupied states and I have a bunch of virtual states. And we're saying that, the clicker wants to behave with me, we're going to remove some lower lying electron. And we're going to ask what happens. Well, first, we can have some electron relax to fill that hole. And I just started teaching quantum in my Gen Chem course, and we taught them that when electrons relax, they give off a photon. Okay, so that's kind of the normal picture. You have a relaxation, you give off a photon. But you can actually have more exotic physics that happens. Instead of that energy of relaxation going to giving off a photon, I can have that energy of relaxation actually be transferred to another electron, and I can ionize another electron. And this is what's referred to as Auger or Auger micron decay. So I have relaxation of one electron, which ionizes a subsequent electron, and I end up with kind of a 2+ state on my original molecule. Now, what happens if I have two molecules? Well, what's kind of cool is molecular clusters really open up new pathways for this electronic relaxation. So let's say I have two molecules, I generate a hole on molecule 2, I can relax down, and now I can actually have energy transfer to molecule 1 and ionize an electron on molecule 1. So same type of picture as Auger processes, but now it's between molecules. And this is referred to as intermolecular Coulomb decay, and has been observed in water clusters and weakly hydrogen bonded systems. It's kind of been proven that this is actually a fairly common phenomenon in biological systems. Now, on top of this, you can also have kind of a third process where, again, generating a hole on molecule 2, I can actually fill that hole via electron transfer from molecule 1, and I can still then transfer that energy to a subsequent electron and have an ionization event on molecule 1. Now, what's cool about this is depending on which of these electronic decay mechanisms occur, I can end up with a charge structure that's very different. If I do ICD, I effectively have a positive charge on molecule 1 and a positive charge on molecule 2. If I follow ETMD, this electron transfer mediated decay, I end up with 2 positive charges on the same molecule. Now, all of these processes, we're talking electron dynamics. We're talking timescales on the order of attoseconds to tens of femtoseconds. So all of these processes really actually happen faster than in your nuclear rearrangement, except maybe hydrogen atom motion. So we, if you want to argue hydrogen atom motion, we can do so. That's kind of where we're moving towards. But besides hydrogen, this is really happening before any nuclei can rearrange. So what ends up happening is we have this ultra fast electronic decay mechanism. We end up with a bunch of positive charge near each other, and we have a Coulomb explosion. And this actually fragments my system. Please.
A question about the timescales. Does it depend on the molecule 1 and molecule 2? I mean, that coupling, that electron transfer coupling will have a time scale that depends on the.
Yes, so of course. So yeah, so you're correct. So depending on the strength of the interaction between molecule 1 and molecule 2, I can have a different time scale. The relative, I'm talking order of magnitude here. So order of that relative, I'm not going to shift from femto all the way to pico, but that'll be the difference between 10 femtoseconds and maybe 100 femtoseconds. Right, this is so in that case, but yes, of course, the nature of the molecular system and the molecular dimer very much affects the process, and whether you might follow this versus whether you might follow this, and as we'll see, also will indicate how well our simulation might be does. But what's cool about this is, so this leads to this electronic decay mechanism and leads to these fragmentation processes. Well, I'm actually going to come back to that. And that's actually what motivates all of this, is these fragmentation events lead to actual very strong kind of decay process or damaging processes. So people are very interested in this as one of the kind of decay processes or damage processes within DNA or biological tissue, where you have these hydrogen bonded systems. It's also very common in surface science. So here to kind of pull this picture, what we have is basically a water molecule on this oxide or this bomite surface. It's an aluminum oxide surface. And if you generate a core excitation within the surface, you can actually have different fragmentations of your water and this surface. And so we're actually collaborating with Tom Orlando at Georgia Tech on this, who's kind of a surface scientist and an astrochemist. And so this has a lot of importance on the surface science within kind of astrochemistry, where you can generate these high energy excitations. Now, what I find really exciting and really cool about this, though, is this is actually a unique situation where it's actually the ultra fast electron dynamics that governs downstream nuclear dynamics. Usually, we ignore, you're trying to do some ionization event, and you just kind of ignore all of the stuff that happens really quickly. You just say, I'm going to start off on the +1 state, in a ground state, Born Oppenheimer, or an exciting +1 Born Oppenheimer state, and then I just watch my nuclei evolve. So I can usually ignore all of the ultra fast electron dynamics, interaction with the laser field, all of this. You can't do that here. So this is kind of a unique situation where really the electron dynamics governs all of the downstream fragmentation. And because of that, it's also a unique place where simulation methods can play a very strong role. Because experimentalists, they tend to measure the downstream fragmentation event. They use mass spectrometry, something like this, and they get the fragmentation events, but they have no idea what's happening at that atto or femtosecond timescale. And so this is really where real-time simulation methods can really play a strong role to understand what's going on in that situation. Of course, I should make the comment that, 2 weeks ago, people won the Nobel Prize in physics for attosecond scale spectroscopy, but one that's, becoming more and more common, but two, it also is an area where we can connect with experiments.
What's the timescale for the electron to come back?
For that secondary electron.
No, for the, I guess you're really excited, inner shell electron, that electron, does it really come free or is it just take some time, but just coming back to the ion?
Are you talking about this electron up here?
The initial process,
This one here?
yeah.
So
When you create the hole, where the electron?
So this electron really gets ejected, right? Because here that one goes away very quickly.
Ejected, you mean like,
Ionized.
free electron?
Becomes a free electron. So this, the electron that I'm basically ignoring here that used to sit in this hole, right? And this is a inner valence or a core ionization. So I'm shooting this thing with an X-ray. So that electron leaves the system very quickly. And so I effectively can ignore that electron. And then you kind of, and like you would do any kind of ionization, right? If I'm ionizing my system, usually if I'm doing that with a laser pulse or an electron beam or something like that, that electron has a lot of energy associated with it and leaves fairly quickly. Okay. Now, counter to that though, this secondary electron, which within our simulation methodology, we are not treating. I'll tell you how we're treating it because that's actually very important. But what's interesting is this secondary electron is actually a relatively low energy electron. So it's still considered a free electron, but it's relatively low energy and can actually go and do, and people are very interested in the behavior of this low energy electron, especially within this like DNA system, because those low energy electrons can go and just wreak havoc from a chemical point of view, right? It's basically a free radical with very low energy. So that's another point of interest, is trying to understand the behavior of that secondary electron.
So I guess the decay of the high energy electron to fill in the hole can take typically at a second.
Right. So what I'll show you is the
Yeah.
time scale that we're looking at is kind of on the order of maybe tens of femtoseconds,
Okay.
5 to 10 femtoseconds. And that time scale will, depend on the nature of the system. So yeah, our goal is really to directly simulate these competing and ultra fast decay mechanisms, and we really want to do this in real time. So this is just what I enjoy doing. I like direct simulation methods, so I don't have to make any a priori assumptions about what's happening. Because as we'll show, we can actually observe other kind of competing effects, such as charge transfer or hole transfer, as these other kind of more rate limiting steps are kind of or limiting things. So how am I going to simulate this process? So we're actually within the context of this, I was trying to do this in collaboration with experimentalists. So we're taking kind of a very, let's say, practical approach, and we're just going to kind of throw real-time DFT at this problem. Okay. But there's some choices. We have to do this intelligently. We can't do anything we want. But I will also state we are throwing real-time DFT at this problem. So I'm also not going to expect to get ever bang on with experiment. Really what I'm going to show is that we can capture the essential physics and we're getting the right time scales for these processes. So what are we doing? Well, first, real-time TDDFT here. And so this is, I really hate that they called linear response TDDFT. It adds just too many letters to the alphabet soup of electronic structure, but I do want to emphasize that here we're actually running dynamics. We are not just doing an excited state method So, distinguishing between linear response TDDFT versus real-time TDDFT. But enough of me complaining. So here, real-time TDDFT, this is written kind of in the von Neumann form. So I'm propagating my density matrix as a function of time, just using my DFT like Fock operator. And then I have my usual terms here, and we'll come back to what we're dealing with in the exchange correlation here, actually, right now, actually, is the next point. So one key thing we have to do when running this is make some appropriate choice for our functional that we want to use here. And here we're really building off previous work out of Ken Lapata and Neri Galvin's work on they've done a lot of work on using real-time TDFT to simulate X-ray spectroscopy. And so we're using and building off a lot of the choices that they found worked in that context. And specifically, we're using tuned long-range corrected functionals to kind of accommodate this charge transfer dynamics. And we can kind of show that this choice, one, as long as we stay within this set of functionals, we're pretty robust. So we're going to show results using LCPVE star, meaning that it's tuned, but we've also done CAMD3 lip, and we're showing basically fairly independent results within those choices. You will find papers that if you use a kind of lower rung, let's say, or stuff without exact exchange, that DFT will not actually get Auger dynamics right. So really moving to these long-range corrected functionals, getting that correct asymptotic limit in long range seems to be key. Okay.
So is it possible to derive that, or is it you kind of use it as a starting point?
So is there a reason to derive why this works, like from a formal perspective?
I mean, you start from, let's say you start from the Many-Electron, the quantum equation. Then is it really, I mean, but then you are talking about the density matrix. Then it's an equation, quantum equation for the density matrix with kind of effective single electron terms. So does it really come from the rigorously?
So are you talking about this equation here?
Yeah.
So actually the formal derivation of this equation, so all right, let me be careful about this. So because I can write the analogous equation for time dependent Hartree-Fock, and then it's just the regular Fock matrix.
Okay.
That equation just comes from the time dependent variational principle.
Okay.
So you just if you assume a single, so you kind of use the same type of idea. Now, real-time TDDFT has more formalism in it than just from the time dependent variational principle, right? You can have Gross's theorems of within the time dependent, and you can show that the time dependent density can be represented, or a time dependent, and Michaela, you probably know more about this than I do. I'm just diving into DFT. I am not, by no means am I a DFT expert.
Polynomial of the.
But this is the Concham,
Yeah, I
this is
know.
the Concham
Sure.
density matrix, which
Yeah.
is not the real.
Yeah.
Right.
Yeah.
But the diagonal, I mean
The density,
the diagonal in the, not in the AO base, but diagonal in the orthogonal base, that's correct, right? That's real.
Sure. Yeah.
and so I'll actually come back to some of those points throughout here. And so I should be covered, right? So this is not actually, and I think I said quantum Louis like, because this is not technically the quantum Louis equation,
Okay.
right?
Yeah.
Because this is the Fock operator here in the one idea, right? The quantum Louis equation is for the full density matrix, not the reduced density matrix, right? And within time dependent Hartree-Fock, which is a little bit more formal in that case, it's coming from the time dependent variational principle.
Yeah,
And you end up
I
with
would
the
say
same
that even that is approximation.
So that's an approximation,
Yeah.
but it's the time dependent variation. It's
Yeah.
a time dependent variational theory, or another way to say it is you're basically at each time step you're always projecting back onto your single Slater determinant answer,
Mhm.
or you're kind of the tangent space is what it is. There are like a few different ways to kind of derive the same thing, either projecting back into the same space at each time, or kind of eliminating away from the tangent space, or just using a variation principle. So like I think it's direct Frankel variational principle. So that variational principle actually is what's invoked in a lot of times. So you can do that, for example, to derive time kind of CAS SCF. And it's the same formalism that you get out. I apologize. I should have shut that off.
That sounds like a nice question that is raised.
Oh, yeah. It's classically isomorphic. It's we're writing up another paper there. Someone grad student. It's his first paper, so he has all sorts of questions. Write the introduction to a paper.
So it's unrelated to your talk.
So that one is unrelated to my talk. Yeah, but that's actually So, but if you do want to learn, that one's actually it's a fun.
But
Fine,
approximation rate is for the time dependent DFT part is the adiabatic approximation, right? Basically, there's no memory in the time. Ignore memory.
So that is correct. I within the functional, I am using a time local function.
Yeah.
That is correct. And that's obviously something, well, I will not discuss that because I mean, there's no one's figured that out. Everyone does time local functionals because time non-local functionals they exist, but I guess maybe NEPA, I don't know how much NEPA works with time non-local functionals. Either case, you're completely correct. One thing that is even within this functional choice, I am using a time local. Okay, that of course is not inherent in this equation here. Right, I could have a time non-local function within. Okay, so, but this is an important thing to note, if, we are using these two long-range corrected functionals to really account for the fact that we are looking at some, inherent charge coupled dynamics within the system.
Just to say something about this long range correction, why is it important asymptotic behavior? Because the plane quantum potential, I mean, again, the self-induced error in the, So the electron, when you pull it far away from the system, it does not see like a 1/r potential. I mean, because the electron, if you are far away from the system, you should see an ion, right? You see your opposite charge. So the quantum potential should be 1/r in the long range. I mean, if the total potential should be just 1/r, because simple quantum potential. But because of exchange coordination, I mean, approximations, it does not see this 1/r. Decay much faster than 1/r.
So that's what these long range corrected.
Yeah, that's why you need this. I'm just saying.
Yeah. So that's exactly.
And it is rigorous proof that hydrophobic is 1/r.
Right. So that's exactly right. So this is getting us that long range asymptotic limit by doing the long range corrected function. Yeah. That's good. Though this then boils down to the other choice of, well, we have this ionized electron, right? And I'm not talking about the first one. The first electron I'll tell you about in a second, but it's this secondary electron, right? We have this secondary ionized electron, and how do we deal with that secondary ionized electron? Okay. And the main issue is we're going to be running real-time DFT in some fixed orbital basis. So I don't actually have an ionization continuum, and I really don't have anywhere for it to go. I really have a finite system. So what we're going to do, and this is again, nothing new. This is one of these projects where we're not actually doing anything new. We're just taking a bunch of different stuff and putting it together in a clever way to get something that's kind of new and exciting by making a fancier puzzle from a bunch of puzzle pieces that other people have done. But here we're going to use something known as a complex absorbing potential. And really what a CAP does is it mimics the behavior of an ionization continuum by introducing non-Hermitian terms in my dynamics. So I'm just going to add an imaginary term to my Hamiltonian or to my Fock matrix. And so I'm going to get some modified equation as such, where we've really introduced this I gamma term, where gamma is called this damping matrix. Okay, and so these non-Hermitian methodologies exist both in the static electronic structure community, for example, to try and simulate resonance states, as well as within the dynamics community to kind of try and simulate open quantum systems. And this is really what we're doing in this context here, is we're trying to simulate an open quantum system. We have this secondary electron that's getting ionized. It needs to somehow leave my system so I don't have artificial interactions with that secondary ionized electron. And to do so, we're going to include this cap. So a few more comments on exactly what the form of this damping matrix looks like. So we're working, so all of my simulations are actually done in a AO basis, or we're not working in a plane wave basis. We actually are working in a Gaussian basis, just for efficiency. I should also make a comment, because I don't think I have it on the slide. All of this is actually we're running an NWChem, so that's the simulation package that we're using and kind of modified and kind of tweaked to do what we wanted. I don't think I actually say that on the slide, but I should. In either case, so we introduced this gamma matrix, which is going to be diagonal in the molecular orbital basis. And I should be careful that this is the molecular orbital basis defined at time t equals 0, i.e. the molecular orbitals we'll get from our initial kind of SCF calculation. And that's kind of what we'll be projecting everything back on. And so we have this diagonal matrix with these small gammas. And pictorially, what we're effectively doing is we have, you know, our occupied space and we have our virtual space. And we're essentially just partitioning our virtual space into a set of orbitals, which we still consider to be bound virtual orbitals, and a set of orbitals which we're going to be higher in energy, and we're going to define this kind of our artificial continuum. Such that this matrix, if we are within this kind of below this cutoff energy, does nothing, so they just are regular virtual states. And if we're above this energy, we're going to have some exponential dependence where this gamma is just going to get larger and larger as we go higher and higher in energy. And what this gamma does is it actually just controls the time scale for how quickly we effectively remove electrons from this system. So by running these non-Hermitian dynamics, we're essentially pulling electrons out of the system. And if this gamma term is higher, we're pulling them out faster and faster. Okay. So that's what we're doing and how we're treating the secondary electron. That we have some choices on how to take these cutoff energies and this zeta term. We're following again a lot of the work that Lapata has done. I have some backup slides if you want to know some more details about that. But there's some prescriptions on the kind of how to choose these, and we've also shown that a lot of our results are pretty robust with respect to those choices. Okay, so the last thing that I need to bring up, though, in terms of the simulation methodology, is how we're actually going to perform this analysis. And this is kind of unique to kind of how people think about this Auger dynamics, but is also important. And so the first thing is that we're going to use the water dimer as an example. And if we actually look at, if I run just a straight DFT calculation on the water dimer, I get a bunch of delocalized molecular orbitals. Well, the picture I drew of these ICD and Auger-like dynamics and how experimentalists think about this process is in terms of kind of localized orbitals. Okay. So a lot of the results I'm going to show is we're going to actually perform analysis by looking at the population of localized orbitals. And here we're just doing something fairly simple because we're lucky we're looking at weakly bound systems, so we don't have to do anything too fancy with localization. We're just going to look at or define a set of localized orbitals by just the molecular orbitals associated with an SCF on the isolated monomer. And so we're going to use that kind of as our basis of analysis. And so we're going to project or rotate, however you want to say it, back onto that basis to look at the mechanistic information. That being said, it's always important to realize, any basis I choose is independent. So in principle, we should be able to see mechanistic information that is, of course, basis independent. And I will show some cool results that don't actually depend on what basis I'm performing the analysis in itself. So to kind of summarize the simulation protocol, and again, our goal is to capture this, for example, intermolecular Coulomb decay process. First off, initial state of the system. Here we're going to be looking at dimers. So we're going to obtain our nuclear geometry from a global minimum at some high level of theory, CCST parentheses T, and then we're going to fix our nuclei, right? So here again, no nuclear motion. We're then going to run a ground state DFT calculation on the dimer using LCPBE star. So again, star because we're tuning that range separated parameter. And this is the basis that we're using. One thing to note is that having diffuse functions is key to this. We actually have this long range interaction effect. So we do need to include diffuse functions in this context here. Here we're only going to be showing results at double zeta because we're running dynamics, so we want something kind of cheap. It has been shown that it's kind of a funky thing. Double zeta does decent, triple zeta does bad, and then QZ does well again, and the DZ to QZ is fairly comparable. Yeah.
Do you need extra diffuse function?
Do I need extra diffuse functions?
You write like D on, looks like even more diffuse than on.
This is me not no. I don't remember off the top
Okay.
of my head.
But essentially diffuse function is very.
Yes. And it turns out though, you actually only really need diffuse functions. So if I'm ionizing initially molecule 2, I really only need the diffuse functions on molecule 1, which is kind of interesting. I don't happen to need them on both. So we get away with just running the diffuse functions on what we call our target molecule, the one that's going to be ionized. If you do not include diffuse functions, though, it does not work. You basically underestimate this energy exchange interaction, and you won't actually see the process.
Could it mean that you like to have some diffuse D functions, or is that what you mean?
Yeah, I might have double. I'd have to ask. I'd have to double check with my postdoc.
Whether that's important or not to have diffuse D orbital with
Sorry, say that one more time.
Having diffuse D function, is it important for the process or?
I don't think I have diffuse D functions. Unfortunately, this is one of these ones where I'd have to double check.
I have a question.
Please.
So when you generate your complex absorbing potential,
Mhm.
I'm assuming that's basis set dependent.
So as in which basis I employ my cap within? Or what do you mean by basis?
Or you pick a basis set and then you do your cutting of the virtual orbitals, but the virtual orbital character would depend on the basis or right, or in the number, and therefore your complex absorbing potential, because you take all the virtuals from a certain point all the way up, right?
Mhm.
So that's definitely dependent on the basis set, right? So
Right,
could it
so-
be the shape of your complex absorption potential that?
So the cutoff energy, effectively, where we choose the cutoff energy, is not that basis set dependent.
Right.
Right. But you are correct that we will have more valence states above it. So, and the nature of those valence states will change a little bit. However, again, because we have not actually observed too much dependence on the basis, because effectively all that's happening is as long as we're getting electrons above the cutoff, we just need to pull them out. Right. And as long as they're just getting pulled out and not having an artificial, really our goal is we don't want an artificial back action of what we're calling an ionized electron on our system. We don't care so much about how that electron is removed from the system, right? And so this is, it's the questions we're trying to ask is we're trying to maintain our focus into this region, and we want to understand this. We're not really asking so much about what happens to this electron. Now, this is still a really interesting question. And, that's something we'd like to do. But I think to answer that question, you'd have to move to a real space implementation. And then you would do a real space cap, which would be at just kind of the edge of your box. And people have messed around with that in their own. There's just real space, real-time methods. I mean, I guess you'd probably know better, but real space, real-time methods can become very expensive. And so that's why by maintaining at least within the MO framework, it's a little bit faster, at least for the first one. But that is an interesting question. So now comes the other question, well, how do we actually generate this initial state? And here we're doing something fairly simple. We're basically running this, ground state DFT calculation, and then we're just manually removing an electron from the corresponding inner valence orbital, i.e. we have a density matrix, and I just have a density matrix which has a 2, and I change that 2 to a 1. And this is actually very easy for us to do because we're looking at, lower energy orbitals that are inherently localized. So we don't actually have to worry about doing any kind of localization or anything, even in the dimer calculation, because we're looking at weakly bounded monomers at low energy states, and we can actually pull this out. This is in comparison to people who look at, for example, just hole transfer dynamics and stuff like that, where if you have a hole actually in your valence state, generating that initial state can actually be challenging, and people are trying to do that with constrained DFT and all sorts of other stuff. We actually get to avoid all of that just due to the nature of the problem. So that gives us our initial state. We're then going to run real-time TDDFT again with this cap being employed. Here's a few different details here. Our time step is basically 1 atomic unit, so 24 attoseconds. We're using a second order Magnus integrator for things interested in that. And lastly, we're doing this orbital population analysis where, because these valence states are delocalized, we project back into the orbitals of the monomers. So anything that I'm talking about in terms of population of molecular orbitals, this is really the analysis that we're doing. So with that in hand, let's start looking at some results. And here we're specifically going to start off with looking at the water dimer, one of these kind of quintessential examples here. And I want to show that really we're capturing this intermolecular Coulomb decay. So as a reminder, molecule 2 loses an electron, or basically relaxes an electron within molecule 2 and ionizes molecule 1. So effectively I start off with a +1 charge on water 1, and I still end up with a +1 charge on water 1 and a +1 charge on water 2. And so what I'm plotting here is the charge loss on both water molecules and the total water molecule. So here, this data is basis set independent, right? I'm not looking at any occupancy. It's just the total amount of density on one monomer versus the other. And what effectively you can see is water 1 stays at effectively +1 charge. That's what we'd expect. And water 2 is getting ionized. Okay, so we're very clearly seeing an ICD-like mechanism. So this is pretty exciting, right? We started this project. It was not guaranteed that DFT was going to do this. We're going to show some results where DFT does not, is going to break down. It's DFT, it's going to break down somewhere. And so doing this was super cool. It's a non-trivial result that we're able to do this within DFT. Okay. But the fact that we're going to be able to do this with DFT really is very exciting, and it's really going to hopefully open the door to do a lot of fun science. Now we're doing real-time dynamics though, so we can actually start to examine what's happening at a much deeper level. Oh, and actually before we get to that, so are we doing, how good are we doing? And again, we're not doing crazy in-depth, we're just kind of doing sanity checks here. Because I don't expect to get bang on to an experimental number. But here, looking at the water dimer, what we're finding is that this ICD process should really happen on a time scale of less than 50 femtoseconds. And here we're really seeing, if I'm looking at this, where this ICD process is maybe taking 20 femtoseconds or so. So we're really kind of in the right order of magnitude, right ballpark to be capturing the right kind of Coulomb interaction between molecule 1 and molecule 2 and the right time scale of this ICD process.
So there's an oscillation come from?
So we will talk, so this is a good question. So we will see some of these oscillations here. Some of these I think are just kind of artifacts of a small basis, in that this artifact is just charge transfer, and is probably, we're looking at a dimer here. So what you'd end up with is a hole here and a hole here. And I can just have back and forth electron transfer between these two things. And so I think I'm just seeing a Rabi oscillation due to a finite basis. Because a lot of these fast oscillations, those are the things that tend to be basis set dependent or functional dependent. But that's, I think, because they are just artifacts of a finite size system. I will show some results where we see some more slower and smoother things where that's not so big. And effectively, I mean, you see a lot of this behavior, and we'll show some of this later. Anytime you're just kind of doing approximate real-time methods or in finite test systems, you see these artificial frequencies kind of appear.
But the thickness of the line means something, or?
I think there's actually even faster frequencies kind of under the hood there that show. Are you saying why like this red line, this blue line over here looks thicker than this red line down here? I think because you're even seeing like really quick frequencies there associated with just finite size. Okay, so we can actually look at the mechanism associated with this, and here I'm plotting the time dependent orbital occupation. So here, this is a very messy plot. We're going to walk through it, but what we're plotting is actually the occupation of those localized molecular orbitals. So to walk through this plot, first, what we start off with, and so this is the population, we start off with our whole generated in this kind of water 1 2A1 state, or it's kind of the oxygen 2S like state. So that was my initial condition. I generated a hole in this system. What we observe is this red line decays. This red line corresponds to kind of a water 3A1 or a water 2P like or oxygen 2P like state. And so the electron relaxes from this state or this orbital to fill this orbital. So red line goes down, orange line goes up. Okay, that's that initial electron relaxation step. And then simultaneously to that, I have these green and blue curves that both drop. And these correspond to P-like orbitals on water 2. And so essentially, as my electron relaxes down, that energy transfers and ionizes out of both of these 2p orbitals here. So this is an ICD process, but here when we look at these molecular orbitals, we're kind of seeing which specific orbitals are playing a role, and we're actually kind of ionizing out of 2 localized MOs and kind of a delocalized. But this is just kind of showing, what kind of information can we actually get out of this real-time simulation methods. And we're showing that we actually do quite a good job looking at this water diagram.
So that's the sensitivity, that's water distance.
Oh, the distance. That's a good question. What is the equilibrium distance?
2 points out.
Yeah, I want to say around 2-ish or something, 2.3, something like that. Something like that. Yeah, and so we should, we're also only looking at one water, this is going to open up a bunch of very low hanging fruit of looking at what happens as we move the water molecule around and that behavior.
So it's purely Coulombic, or isn't there some exchange interaction effect?
So it depends, I guess it depends on what formalism you wanna look at. So actually, I should be careful here. So I think at this distance, we are far enough where I think it should be Coulomb dominated. So within ICD, if you actually work out the formalism, you can basically get 2 terms. One that's Coulomb dominated and should decay as 1/r⁶. And so this would be analogous to your Forster style energy transfer. And then you should have an exponentially decaying exchange term, which would be like a Dexter style energy transfer. Here, I believe we should be Coulomb dominated, but don't quote me 100% on that. So here we've talked about water dimer. I'm also going to discuss one other example in kind of detail here, which is the argon water dimer. Okay, and same type of picture. We're starting off with this charge loss. Effectively, we're starting off with a hole on argon, and then we're going to ionize our water molecule, and that's what we essentially observe. Argon kind of stays at 1, and water gets ionized here. So we're still seeing ICD, but here we're actually observing something more complex. And this is really where we can emphasize the benefit of these real-time simulation methods, where here we're actually seeing this oscillation, which is much smoother and does not look like, these ultra fast oscillations at the end. So this is something I expect to be more physical. And so here we're actually seeing a simultaneous or competing hole transfer within my kind of inner valence species. So we're seeing electron transfer between a lower lying water MO and the argon, and we'll observe that in a second, that actually competes with this ICD process. Okay, and this is not something that would pop out if you did some kind of Fermi-Golden rule analysis. This is something that inherently you need to really kind of do a real-time simulation method, because you might not guess that this would happen a priori. And so it's by running this direct dynamics that we can start to get at this type of process here. And so we can look at this in more detail, again, showing these kind of crazy plots, but we're showing argon 3s starting off with the hole, and here we're observing a very smooth hole transfer, right? This is now a lower lying water molecular orbital, and we're seeing hole transfer between this 3s and water MO as my electrons start to relax down. So here the red line relaxes down on no, I lied. We're ionizing argon, so it's the blue and green that relax down to fill the hole, and ionizing the red. So the red, blue, and green are the ICD process, and that's occurring at the same time as this electron transfer, hole transfer, depending on which way you prefer to look at it, between the water and argon. And so this is actually, again, pretty exciting that we're able to capture this, because if you're thinking about moving to more complicated systems, so let's say if you're moving to having a water, 3 water molecules, water on a surface, some of these hole transfer events will start to become very important to understand and are competing with all of these ultra fast electron dynamics and ICD. So understanding all of these competing effects and having methodologies that allow us to tackle these problems really is exciting. And so here I want to show, it's always nice to show pretty plots. The fun thing about doing dynamics is in my postdoc now owes me a movie of these pretty plots. But it's also important to, again, show data that is basis set independent, right? So all of this MO occupation does depend on the choice of my basis to some extent, but I really can pull out the exact same physics by looking at basis set independent quantities. And here what I'm actually plotting is a slice of the real space density as a function of time along the plane that connects the water and oxygen. Okay, so and here I'm actually applying the whole density. So what we start off with at time t equals 0 is I have a hole on my argon atom, which looks purely spherical because it's in a S-like orbit. Okay, and I don't have a hole on my water molecule. Then as time goes, I have my whole density transfer from my spherical argon to this oxygen 2s-like orbital here, and we basically get it to go to the oxygen, and then it comes back. So along these 3 curves, I'm seeing this whole transfer between S-like orbitals. Everything is nicely, it's spherically symmetric on argon, and this is this kind of extended sigma-like orbital associated with the oxygen 2s delocalized on the protons. Then what occurs is we can actually see, and it's most clear in the water molecule, we actually start to transition from something that looks oxygen 2s to something that looks oxygen 2p-like in real space, right? And similarly, though less noticeable, we've gone from something that's spherical or circular in structure to something that's not delocalized, but more oval in structure, associated again with transitions to the 2p-like orbital. So this is, I saw this day and I'm super excited. This is really cool, right? This has nothing to do with my choice of single particle basis that I use to analyze the code. This is a true observable. It is the real space density. And we're distinctly able to pull out the same mechanism that we pulled out by looking at the MO occupations, right? We are seeing hole transfer between S-like orbitals, and we're seeing a transition from filling up an S-like orbital to emptying a P-like orbital. And that's coming directly out of the real-time simulation method.
How do you calculate the hole density?
So the hole density is it's literally just 1 minus the occupation squared. So it's literally, it's literally, we're just subtracting the whole density, we're literally just taking the electron density and just subtracting off the electron density for the non-ionized system. So we're basically taking the difference with the full electron density with all n electrons. So here we're simulating basically an n-1 or n-1 to n-2 system, and we're just subtracting off the density for the full n electron system.
You have, okay. I mean, do you do like a neutral calculation, a ground state calculation first?
Yeah, so we have, right, so we have the ground state neutral.
And then you do, you base your, I guess you use your, population of these output and use that as a way to work out, I mean.
Yeah, so correct. So the real space density, we can just basically would just be a sum over the occupation of an orbital times the magnitude squared of that orbital. Right, and so that gives us our electron density, and then we can just subtract off the density from the ground state calculation. So that gives us a whole.
And do you use the unrestricted conjunct solution?
This is all restricted.
Even if you have a odd number electron, I guess you.
Yeah,
And
so,
remove electron, you have odd number, so
yeah, so I think it's restricted on the chart.
you still use it.
Yeah, so we're not doing anything fancy with respect to spans. There's no reason we can't, but with this,
So basically, okay, I'm sorry, when you do restrict you, so you remove electron, you basically just take the, okay, change your occupation from 2 to 1.
Yep. Yeah, that's all. Okay, and then to show that we can do this on a few more systems, maybe this time. Second. What am I supposed to go to? How much? I forgot how long I have. So is it till 5:30?
You have 20 minutes.
I have 20 minutes.
Yeah.
Ooh, I am way behind. Okay. So, well, the second half will just go very quick. Okay, so we've also done this and kind of looked at a variety of different hydrogen bonded systems. So here, this is just a reproduction of the water-water. We've also looked at HF-HF and HF-water. We're effectively seeing the same trends. That's really what I kind of want to show here. Though, Michele, to your point here, you can see that these time scales of all of these ICD processes does vary with the nature of the species we're looking at. And on top of that, here, if for an asymmetric species or, well, all of these are actually asymmetric. These are all hydrogen bonded. So these are all actually when we generate the initial hole on the hydrogen bonding donor. In comparison, if we generate the initial hole on the hydrogen bonding acceptor, we actually see different behavior. This tends to be a weaker ICD process. And so here, for example, you can see that this kind of is done before, whatever, let's call this 17 or just below 20 femtoseconds. Well, here, this ICD process really doesn't plateau till close to 30 femtoseconds. And this is what's also kind of observed by other theory experiments. If you actually ionize the hydrogen bonding acceptor, it tends to be a weaker ICD process. The last one I'll point out, which is kind of interesting and we don't fully understand, is if you actually do HF water, here we're actually seeing a distinctly different mechanism. We don't actually observe ICD, we're actually observing electron transfer mediated decay. That's why we're seeing this red drop and this blue increase, but the total, the net ionization is still kind of on the order of everything's just below +1. We don't actually perfectly get the full ionization because we're running real-time dynamics here. It's not necessarily expected. So this is actually kind of an interesting question that we're kind of fully analyzing here. But the main take home here is we're really able to show that at least within these hydrogen bonding structures, we are able to capture this ICD physics with real-time DFT. We're getting the right time scales, we're seeing the right qualitative trends. It seems like with the choices that we've made, we're really able to start to capture this physics. And so, we're very excited about this. We're going to start to kind of run the bank on this, so to speak. Look at how transferring a proton actually can start to affect this behavior, how different rearrangements, different molecular clusters start to really affect this dynamics. Now, everything is not hunky-dory. Again, we're doing DFT. Things do break down. So where do they break down? So they tend to break down if the interaction between our two molecular species is very weak. So if we have basically just purely van der Waals dominated systems, we just are not able to capture the ICD process. Neon argon is actually one of the quintessential examples to show ICD. So a lot of the theorists who kind of discovered it and really pioneered the theory behind ICD is Cederbaum, and he's published tons and tons of papers on the neon argon system. We're not observing that. We don't get ICD. All we're seeing is if we generate a hole on neon, then that energy just goes straight into neon and just ionizes all sorts of wonky electrons. And effectively, we're just boiling off electrons from the system without particularly any correct physics. And if we look at neon water, we literally see nothing happen. It just stays flat. And this is just as the interaction between our systems becomes weaker, DFT just isn't able to appropriately capture these interactions. This might not be too surprising, the ability for DFT to get van der Waals interactions right. This is obviously challenging. I should mention, because I need to add that to the slide, we are adding Grima's D corrections to these calculations to get some of this stuff right. So we do have dash, I think it's dash B3. But even so, we're just unable to get this stuff correct. That being said, though, in summary here, by really combining real-time DFT with these complex absorbing potentials, using these long-range corrected functionals, we really are able to show that we can accurately capture ICD within these, weakly bound systems, as long as the strength of the intermolecular interaction is relatively strong. So if we really stick to hydrogen bonding systems, or I showed water argon. Argon was large enough that interaction is strong. If we stay within that class of systems, we're able to get things pretty darn. If you move to too weak of systems, that's when things start to break down. And we have ideas or pondering ideas on how we might be able to make some kind of quick ad hoc fixes. Adding kind of maybe some screened Coulomb terms within the real-time TDFT to account for some of those facts.
So what about the real density van der Waals function?
So there's no question you could, the correct thing would be to get a better functional. that's something I personally do not want to do. I don't want to dive into functional
I'm
development.
just asking you because you mentioned the van der Waals the interaction, I think it might be important because it brings correction with material correction and does not change the electronic structure. Has no effect to the object. And what you're interested in the electronic dynamics, but the density dependent function mean retail, it may have a chance to actually change the electronic dynamics.
Yeah, so you're correct, there's definitely higher level functionals we could do or other corrections to the functional that we could do that might capture it. And it's, it's an open question as to exactly what the best way is to get the more weakly bound systems.
But
So please,
I didn't mean to stop.
no, please,
I don't know if I believe this, because if I think about the decay of the interactions, van der Waals interactions decay, the potential decay is like, what is it?
one of
R,
our six.
which is not 1/r, right? And you said that this Coulomb mediated, which is 1/r, right? So
No, so this is, so the ICD actually goes as 1/r to the sixth.
Not necessarily,
but
because the Coulomb interaction in the long distance limit, it is dipole-dipole interaction,
Right.
but maybe at short range, because it's Coulomb interaction, it can be actually different.
So you are correct. So you do have two terms, right? So if it's purely the Coulomb term, it'll be dipole-dipole and go 1/r to the
Yeah,
sixth.
yeah,
Or you can have the exchange term, which will go exponential.
yeah, and then you can have, at short distance, you can have multiple
you
interaction.
have quadruple.
Yeah, therefore, normally it's actually, as the distance becomes smaller, it becomes more complicated.
Mhm.
And also it depends on the angle.
Yeah, so that's kind of a natural thing would be to investigate how well, like, do we get the distance dependence correct? And that's a natural question for us to explore for sure.
So essentially, you're witnessing the transition between some weird charge interaction that can be quadrupolar or whatever, multipolar, to dipole-dipole interaction. Is that what it is? And then when you are a dipole-dipole interaction regime, it goes like 1/r to the sixth because you have this Foster
Like fortunately.
energy transfer. But that should be captured by RPA, so no exchange correlation. So
So
I don't know what's going on.
so I'm missing the final question. So
So I
are
don't
you
know
asking,
why you don't see anything. I don't know why you don't see it.
so why I don't see anything in the neon argon system?
Right, because you should see it with RPA. Without any exchange correlation.
So it's. Okay, let me think if I have, So we have
If
to
I
be
understand this
careful
correct,
because there is always there is always a some form of correlation because inherently this is a 2-electron process. Right, I have one going down and one going up. Right, so no matter what, even though the matrix element goes as 1/r to the sixth, it still is an electron correlation problem. Because it's a 2-electron problem. If I, for example, if I look at the formal matrix elements associated with this process and that everything is a Fermi-Goldman rule type expression. Right, what I would end up with is my initial state is this whole state, and my final state is 1 electron's dropped and 1 electron's been ionized. So the matrix element is between a 2-electron state, so there always has to be some correlation effect at play. And so capturing this energy exchange between this and this is challenging even in the lungs. So that's my,
I'm not convinced, but it doesn't mean that it's not true, right?
right. So in some sense, the proof is in the pudding in that, like, we
Yeah,
get
yeah.
it right. And so this is to my would be my bet, and what we're thinking is that if we include a screened Coulomb interaction to kind of to get that interaction more appropriate, that we will do better. And you can kind of, and that's motivated by some of the just straight Fermi-Goldman rule work where, if I calculate Hartree-Fock orbitals, I try and calculate a matrix element, I really need to incorporate a screened Coulomb interaction as my transition interaction. So that's kind of the motivation of why I'm making this. But I have no, outside of me thinking like this and the fact that, numerically we're not getting it right. There's no question. And we spent a lot of time. We started off with the neon argon system. We're like, oh, this is way simpler. This will be work, and it didn't work. So it does work, but there are ways there. There are probably a variety of different ways to maybe get it to work. Okay, so in the last 10 minutes or so here, I will shift gears here and I guess briefly introduce this quantum embedding stuff. So the goal here is effectively what I've talked about for way too long, is using DFT to simulate some very ultra fast electron dynamics. However, the question is, can we do better than DFT? Can we develop more sophisticated methods to solve our real-time dynamics problems? And here, what I'm going to very quickly tell you about is our work dealing with quantum embedding and extending these ideas of quantum embedding towards real-time dynamics. And so I'm going to move so we've had, plenty of talks I feel today, and especially when I hinge on Tianyu's stuff in terms of quantum embedding. So I'm going to move kind of fairly quickly. The idea, we have some small subsystem, and we want to basically treat the interaction with the surrounding environment, but do this efficiently, right? That's just the inherent nature of any embedding calculation. How do I deal with this subsystem environment interaction? And what I'm going to tell you about is kind of, we're coming out, to Garnet people. So Jeremy, you talked about DMFT. I'm going to talk about DMET. The key difference here, and I guess I want to make this point because we've had a few different embedding talks. So Chanyu was talking about, or I guess going back to Michaela, who was doing the kind of DFT level embedding. One of the issues with DFT level embedding is you don't get correlation between your subsystems. Now, in dealing with dynamics and dealing with some of the systems that we're looking at, I do want to incorporate correlation between my different subsystems. That's something that inherently I want to be able to capture. So DMET allows us to capture strong correlation between subsystems of interest. That's also what DMFT gets you. The difference between DMFT and DMET, DMFT is Green's functions, DMET is all wave functions. Okay. Green's functions still scare me. So we're going to stick with it. And he's nodding over there. He does it for a living now. And so this is kind of the difference here, is this is going to be a wave function based embedding that allows us to get correlation between our fragments of interest. And it's mathematically based on something known as the Schmidt decomposition. Effectively, the simple math here is if I write my wave function in kind of an expansion in terms of subsystem states and environment states, I have a large number of environment states in principle. However, you can kind of do this tensor network-like trick and do a singular value decomposition of this expansion coefficients, such that you can then rewrite your problem in terms of two sets of states, that basically a new set of environment states, which we call a multi-electron bath. And the key thing here, though, is the number of these bath states is equivalent or equal to the number of subsystem states. Okay, so pictorially, what I've done is I've taken a very large environment and written it in terms of very small environment. So this is the same general flavor as DMFT, but again, here we're dealing with wave functions instead of with the Green's function. Okay. So the good, in principle, we have a method to exactly embed a fragment in a bath of the same size as itself. That's super cool sounding, but there's no free lunch. The bad is, in order to, in principle, get this special set of state, I would have to know the exact wave function. So we're going to use, and here I'll move quickly because this is going to feel very similar to the DMFT stuff. So the fix is, what we're going to do is we're going to perform a mean field calculation on the total system, use that mean field calculation to generate a bath state. We can then do a correlated calculation on the set of bath states, and then introduce some self-consistency. Here we introduce the self-consistency by matching one electron reduced density matrices. So everything's done in the terms of the 1RDM. Now, the goal though is we want to actually take this idea and extend it to dynamics. And so when I initially did this or tried to tackle this problem, I just worried about one subsystem and then one fragment. So it's just kind of a single subsystem coupled to a fragment. And I used basically the time-dependent variational principle to derive the equations of motion. And I got something very analogous to kind of the time-dependent CAS-like calculation. But what I really want to tell you about is kind of our new work where we did this in a multi-fragment form. So very similar to what Michele showed in terms of, multiple different subsystems. So in this context, we'd have one mean field calculation on the total system. We would then take a fragment, and that would be associated with its own set of bat states, and I'd have one correlated calculation on that. Then I take another fragment, get another set of bat states, another fragment, another set of bat states, another fragment, and another set of bat states. And so I perform separate correlated embedding calculations, but all of these correlated calculations are all coming from the same mean field, i.e. this same mean field is generating all of these bat states. So in some sense, these are already talking to each other in some way through this mean field calculation. And on top of this, I can basically stitch together these correlated calculations to define a global density matrix or a density matrix that describes the entire system at this correlated level. And then I introduce a matching condition between this global density matrix and this mean field density matrix. And this is how these separate correlated calculations end up talking to each other within this framework. Now, there's a difficulty when I try to do this for dynamics. And so this point I do want to kind of emphasize here. So a lot of, within DMFT and within DMET, a lot of these matching conditions are done numerically. A numerical matching condition does not work for dynamics. It works within a static framework because if I have, at one SCF step, if I have a matching that's not so good, I just go to my next SCF step, and the next SCF step will probably fix it. In dynamics, if I ever have a matching that isn't so good, well, my dynamics will start to diverge, and it'll never come back because I have a deterministic method. So having a numerical matching just does not work for dynamics. Okay, and the kind of conventional DMET uses kind of a numerical matching. And on top of that, I also can't use the time-dependent variational principle in the context of multiple fragments because I don't actually have a single wave function anymore. I just have this single density matrix. So we had to come up with something new. And what we did is we utilized, or we took advantage of a different form of DMET known as projected DMET, which actually has an analytical matching condition. And so the relationship between this global density matrix and this mean field density matrix is actually done analytically. And I'm gonna, because I think I'm probably just about out of time here, because I want to show some results. So if you want to know more about that matching condition, because I'm gonna have to skip the slide that goes over that, just ask me. But the key idea here is then, given this analytical matching condition to actually run dynamics, what we're going to do is we're going to simultaneously propagate a mean field dynamics for my total system, and then we're going to simultaneously propagate a dynamics for each of these correlated states. So I basically have this kind of very parallel structure. All of these things are going to be propagated directly, and then the equations of motion that I derive to govern this dynamics are going to enforce our DMET matching conditions. So they're going to enforce the fact that these bath orbitals should come from this mean field density matrix, and the equation of motion should enforce that this mean field density matrix should come from this global density matrix in this way that I haven't told you. Okay, One thing I want to emphasize though is this does not mean we're performing a self-consistency calculation at each time step. We are performing a purely deterministic method. It's just that the equations of motion inherently have this constraint built into them from the get-go. It's effectively like introducing a Lagrange multiplier into any kind of minimization or something like that. So no SCF, purely deterministic method that enforces these constraints, and we have this parallel structure where we're doing mean field dynamics and correlated dynamics simultaneously. Okay, and so that's where we're going to kind of leave the theory at. So I'm going to skip this slide that goes over all the details between that. Very quickly here, we'll just kind of run through some data. So here we're looking at the single impurity Anderson model. We basically have a single site that we're going to suddenly switch on electron-electron interaction. All of the results I'm going to show, we're going to start with a non-interacting initial guess. The reason for that is then all of the methods that we're looking at are going to be exact at time t equals 0. So all of the comparisons are just associated with the dynamics. This is important because if we had interaction, then Hartree-Fock would just be useless as a comparison here. So here I'm comparing the exact result, which is coming from time-dependent DMRG to time-dependent Hartree-Fock. As I increase U, my electron-electron correlation becomes stronger. Time-dependent Hartree-Fock gets worse. If I look at the real-time DMET results, as I increase the size of my subsystem, we actually can see a very nice, smooth convergence to the exact result, even outside in this strongly correlated regime up here. And now we have this multi-fragment structure. So what's nice about this is we can look at not only situations where we have one important point of region, but we can look at, more delocalized or extended regions. So here we're now looking at a multi-impurity Anderson model where we have this interaction term evenly distributed through the system. We're similarly seeing very good behavior. The one I'll dwell a little bit on is we can also look at a disordered system. So here we now have randomly placed our different places of interaction. And if we, let's say, look at this site here, we see very good behavior. And in comparison, if we look at that site over there, we also see good behavior. And so this is really nice about this multi-fragment method. I'm actually not building in specific accuracy into a specific region of space. We're actually getting good accuracy over the entire region of space. And then we'll have two last slides here, and then I'll wrap up. So here we're actually now looking at driven dynamics. So we actually have a laser pulse that's driving my system. We're only, just to walk you through a little bit, we only induce this laser pulse in a small region of space. And we can look at the behavior across different sites. So here we have the central site where I'm also suddenly switching on electron-electron interaction. Again, this is so we can start off with a non-interacting state. We see very similar behavior to what I've been showing. But what's interesting is if we look at, let's say, this site, which is not the central region, but within the laser region, we can see this driven oscillation. The pink curve is sitting right on top of that black curve. While the green curve is not getting this oscillation right. That's pretty cool and exciting. We're really getting this driven electron dynamics. And on top of that, if we look at some region, let's say way out here, that's far away from the laser region, well, the laser pulse is centered around 5. Well, out here, nothing happens around 5 because there's a delay, right? We're generating an excitation in this region of space, and there's some time for it to reach out further away. And so again, pink sits right on top of black. We're able to capture that delay and these appropriate set of oscillations. And so, this is very exciting. We really are able to capture electron dynamics across extended systems, even in these driven, highly correlated systems. So lastly, we do dynamics. I do have to show a movie. So here, this is just kind of a kitschy movie of a 2D system where we really can't generate the exact time-dependent DMRG results, but this is fun. We basically generate an electron-electron pulse there, electron-electron interaction, and we can see the electron density kind of come off and come back. And we show nice smooth convergence with respect to this as we increase our fragment size. So with that, again, new method, multi-fragment real-time quantum embedding, we're able to capture dynamics across this extended system. And to where we're really kind of pushing this is to really the next step we're interested in doing this is looking at spin non-collinear systems. So really looking at spin transport dynamics in this context to tackle this CISS stuff. And so here's the pretty picture of my group. Daria was the one right there who did the real-time DMET work that I just talked about. My postdoc Yisheng, who's here, in collaboration with James, who's actually in Tom Orlando's group, did the real-time DFT, and then a variety of other people that working on some of these other classically isomorphic methods. With that, I'm happy to take any questions if there's even time.
Okay, thank you. One big question.
So in the single impurity Anderson model, when you're using more than two, so essentially how are you choosing them?
So
Or
the
the ends up,
like where does the site end up? Is that
Yeah.
where you're talking about? So in that case, I think we're literally just going down the line. I'm trying to remember if we might always be trying to keep that
the
Subsystem
interactive sides.
in the middle of our fragment. But I don't think it matters too much. That effectively it converges pretty, in this case, because it's a 1D system, it converges pretty smoothly with respect to how we're choosing our variables. In the 2D case, that's no longer true, but in the 1D case, I don't think that's too much of a worry.
Got it. Yeah, so in the 2D system, you need to choose more carefully.
Yeah, to get a smooth scaling. Or smooth convergence, you have to be a little bit more. As in whether you're doing like a 1x2, 1x3, 1x4 versus a 2x2 polygon.
Square.
Yeah.
Okay, thank you so much. Yeah, thank you.
Supposed to see, but
Yeah.
well, thank you, Steve, for posting all of this.
Yeah, thank you.
Running this.
Yeah, so we will, available for dinner.